Welcome back. We're going to do a second day on regression. Today we're just going to take a look at some different regression models. So in this first example, it gives us a table that shows wind speed in miles per hour and the corresponding wind chill factor when the air temperature is 10 degrees. So we have our table of values. We have for x, which is wind speed, y, which is wind chill factor. We're going to go over to our calculator. We're going to want to put this data into the calculator. So that's stat, edit, and I went ahead and did this already just to save a little bit of time. So you want to make sure that in L1 are your x values, in L2 are your y values. Please be careful because if you are off by one digit, it's going to mess up your entire model. So once you have that in, we're going to go ahead and hit stat, calculate, and let's take a look as to what model they want us to use. So this is different than any of the ones we did yesterday because they're asking us for a log regression equation. So we're looking for a log regression. We'll have to kind of see which one that would best represent. So that's linear, 5 is quadratic, 6 is cubic, 7 is quartic, 8 is another linear, 9, ln. So if you remember, ln stands for your natural log. So ln is your logarithmic regression. So let's hit enter. All of this should be fine, L1, L2, and then hit calculate. So we have our logarithmic regression model. Okay, so let's take a look at our rounding directions. It says to the nearest 10,000. So nearest 10,000th, that's going to be tenths, hundredths, thousandths, 10,000ths. So that's 4 decimal places. Okay, so we have y equals, A is 13.0134, we'll round it down, leave it at 4. Plus a negative 7.31348, so the 8 will round it up to 5. So plus a negative, I'll just leave it as minus 7.3135, and then ln of x. Okay, so that is our regression model rounded to the nearest 10,000th. So we're going to go ahead and use that to answer some other questions. So using this equation, find the wind chill factor to the nearest degree when the wind speed is 50 miles per hour. So if you remember back up here, wind speed is our x, wind chill is our y. So we're solving for y when our x value is 50. So this one's just going to be very straightforward. It's just substituting in 50 for x. And we'll just put 50 in for x. Okay, so we'll go over to our calculator. $13.0134 minus 7.3135 ln of 50. Okay, so rounded to the nearest degree. So nearest degree, that will round to negative 16 degrees. So it was negative 15.59718 ... And we're just going to go ahead and round that to negative 16 degrees. Okay, let's take a look at the last part. So again, based on our equation, so I'll just copy that down. If the wind chill factor is 0, what is the wind speed? So this time we're solving for x, because they're telling us the wind chill factor, or y is 0, what is the wind speed? Okay, so substitute in 0 for y. And then this is where we're going to have to use our knowledge of logarithms from our previous unit. So I have to solve this log equation here. So let's subtract 13 first. So minus 13.0134 from both sides. Okay. So then we want to try to get x by itself. So we have this negative 7.3135 times the function ln of x. So we'll go ahead and divide both sides by negative 7.3135. We'll do the inverse operation. The inverse of multiplying would be dividing. So we'll divide that out. Go over to the calculator. So negative 13.0134 divided by negative 7.3135. Okay. So that's going to give us 1.779366 goes on forever, rational number, ln of x. Okay. So we're at this point here where you might not remember what to do, but hopefully you do remember what ln stands for. ln, if you remember from our previous unit on logs, ln is a natural log. ln is log base e. So it's really log base e of x. Now that we have a log with a base, maybe remember if you're in log form and you're kind of stuck, there's nothing else you could do. If you're in log form, you want to convert to exponential form. So we circle that base and run the race. So we're going to convert it over to exponential form. So e is the base of our log. It is the base of our exponent. So we're looking at e to the exponent of 1.779366 equals x. So we'll go on over and finish this up. To get e, it's second division sign, e raised to the, I'm going to go up here and grab the entire thing. This way I take all the digits and then hit enter. So we're looking at 5.926. And the rounding directions are to the nearest mile per hour. So we're looking at 6 miles per hour. Let's take a look at another one. So we have data collected by a biologist show the growth of a colony of bacteria at the end of each hour. Write an exponential regression equation to model these data, round all values to the nearest thousandth. It may be a good idea to pause the video and try on your own, and then you could kind of fast forward and see if you get it right. Otherwise, I'll just go ahead and do this with you. So stat, edit. We want to clear this out. Don't delete. Clear, enter. Clear, enter. So we'll put in our data. So 0, 1, 2, 3, 4, and 5. Then 250, 330, 580, 800, 1650, and 3000. So we have our data in. We want to write a regression, exponential regression. So stat, calculate, we'll go down to exponential regression. So that's 0. Hit enter. All looks good. Let's hit calculate. Okay. We're going to round to the nearest thousandth, so that would be 3 decimal places. So y equals 215.4 1.983 times 1.652 to the x. Okay. So now using this equation, if this trend were to continue, estimate to the nearest 10 the number of bacteria in the colony after 7 hours. So a straightforward one, we're just going to put 7 in for x, because x stands for time. Okay. 215.983 times 1.652 to the 7th. Okay, so 215.983, whoops, 215.983 times 1.652 raised to the 7 power. Okay, and hit enter. All right. So I don't know if you noticed the rounding directions, but they are a little different than we're used to. To the nearest 10. To the nearest 10. It's not nearest 10th, it's nearest 10. So the 5 is going to take a look at the one over here, and it's going to round down. So it's going to round down, which means that to the nearest 10, it's 7,250 bacteria. Okay, so you just want to be careful with that. The trickiest part was actually probably the rounding directions. Okay, so moving on, we have this chart to the right, shows the average daily temperature each month in Socrates, I think that's how you pronounce it, New York. Write a sign regression equation to model the average daily temperature. Okay, so it's asking us to write a sign regression, so we're looking at trig here. This would be a trigonometric regression. So same thing we've been doing, we'll just go ahead, put in our data into L1, so we'll take a moment to do that. Okay, each month is represented by 1 through 12, 1 for January, 12 for December. Okay. In January, its average high is 34. Next month, 38. So it's starting to go up as we get to the summer months. And then as we get to fall and winter, it starts to go back down. 51 and 39. Okay. So we have our data in. We'll go to Stat, Calc, and let's take a look to see which regression it would be, which would make the most sense. So now exponential, power, logistic, no, sign regression right here. So we're looking at a sign regression. We'll hit enter. And then it has this thing called iterations. Just leave it as 3. Leave L1, L2. Don't even put anything in for the period. If you leave it blank, the calculator will just do it for you. So basically just leave everything in. Iterations just means the higher the number is, the more accurate it's going to get. But just we'll leave it at our standard of 3. Otherwise, calculator's going to take a long time to do it. And then we'll just hit calculate. Okay. And then we'll round all coefficients to the nearest 100th. Okay. So we have y equals 26.02 sine 0.49 x minus 1.86 plus 58.85. So if we just take a look at this, the amplitude is 26, so kind of like our variation. It has a horizontal shift. It's moved to the right 1.86. It has a vertical shift. It's moved up 58.85, and it's going to be represented by a sine graph that's kind of shifted. So there's your equation, rounded to the nearest hundredth. It's not asking us to do anything else with it, so that's it. And we have one last one. So we'll take a look at that. So I went ahead and just put everything and I paused my video and did it just not to waste time. So everything's in. This is the same one where it's asking for a, it's actually not telling you which regression, but we need to think about it. This is temperature. Temperature is, fluctuates. It starts low, it goes high, then it starts low again. So if I were to almost draw this out, starts low, goes high, then goes low again, and starts to return up high, low, high. You kind of get the idea that this is going to be a trig function. It's going to be a sine or a cosine curve. If we want to, we could actually have the calculator plot it for us, which we'll take a look at right now. So we'll have the calculator plot these points for us. If you hit second, y equals, we have these things called stat plots. Let's turn them on because the calculator will start to plot the points for us. So I'm going to turn that to be on. We'll have it just, plot these data points here, so that's fine. Okay, then let's hit zoom. We're going to do zoom stat. This isn't something that you need to do. This is just to show you that it's, there you go. That's your data plotted. That is going to look like a sine curve like I drew before. Continues to fluctuate like that. All right, so now we know that it is a sine curve or a cosine curve. That actually looks like a negative cosine curve. We can go ahead and hit calculate, and we'll go to sine regression. We'll leave this as 3 iterations, just leave everything as is, and hit calculate. Okay, so we'll just go ahead and round everything to the nearest hundredth. So y equals 25.61 sine of 0.51 x minus 2.07 plus 56.88. And that's rounded everything to the nearest hundredth. Okay, so at this point we're done with regression. It was a very short little topic. And that's it. We're going to move on. All right, have a good one. Bye.